Okay, so I want to tell you a few words about reinforcement learning. So what is reinforcement learning? The basic question. So someone can say that it's simply a model of the world, but it says pretty much nothing, like physics, a model of the world and how we interact with it, and maybe biology or pretty much everything we do in computer science is in a sense a model of the world. But reinforcement learning focuses on us, on agents which interact with the environment, and the environment. It's somehow separate. You see the barrier between agent and environment. We do make an action, and the only what we get from an environment is the reward. And what is a reward is up to some interpretation. It's not straightforward what's a reward in the environment. Of course, in the end, we also get another state of the environment. So games are pretty similar in the sense that we interact with some environment in the game. We usually get a very simple reward in terms of points or any other defined reward, and the agent is a player. So how I like thinking about reinforcement learning, there must be some learning. It's reinforcement learning, right? So how do we learn when we interact with an environment? It's a basic question. And the whole machine learning is about learning. And so how is reinforcement learning special? And I like the comparison to the game Child's Play Hot and Cold. You move around the world, and the only information you get is hot or cold, whether you're happy or unhappy, whether you got a reward or not. So that's pretty much the only information. And there's an action we make, there's reaction from the world in a sense, and there's a modification. And what's the modification? We think about modifying our behavior so that we get more reward. And the basic, say, toy problem in reinforcement learning we may occur is navigation problem, and it has many flavors. One of them is we'd like to get to an exit point. And why would we want to get to an exit point? We have to define somehow the problem. So when we move, we get a -1 reward. And when we get finally to the end, we don't get any reward. In the end, we get 0. It doesn't make sense to you. Yeah, in a sense, it does, because at least you don't get minus reward for walking. If you get to the end and you stop walking, in a sense, you may define the problem that infinitely you get zeros in the end. Okay, so it's one formulation. There are many others. You may get, 0 for the walking, 1 in the end. So it's quite sparse. Okay, when you get 0 when walk and 1 in the end, the reward is very sparse. You only got the reward in the end. So it's a slightly different problem that when you walk, you get -1 and 0 only in the end. And why do we say like reinforcement learning or we would like to use it? One thing is that it's closest we've got. Okay, someone may disagree, but it's close to how we think, how we act with the environment, in the sense that it has an easy formulation. Like I said, it's only this hot and cold problem, in a sense. And it's very general. Since it's easy formulation, in general, it's pretty much the same. So I'm too good for you, and I'm not even that good. Yeah. Why? There are areas of active research in reinforcement learning. One of them is effective exploration problem. The other is how our agent, which is interacting with an environment, can generalize what it has learned. So imagine I can learn how to walk in this room, but does it really apply when I go out or to a different room? There are safety issues. I won't talk about that today, and there are many, many more. It's very active, really. And we'd like to learn something. We'd like to learn some behavior. I don't want to scare you with maths. We won't get deep into the algorithms today, but I'd like to mention that we have a policy with respect to which tells us how to behave. So we'd like to behave somehow in the environment, and we'd like to optimize our behavior. So the Pi is a policy. It has some parameters. It's a model of how we behave. And when we give the policy the state, the current state of the world, and an action, so we ask, how likely am I to make this action? The policy gives us this information. Okay, we may think of the policy as given the state, you have few actions, options, and policy says whether I'd like to behave in the way or not. It gives me probability that I will make this action. It gives me the probability distribution of the actions. There are other techniques based on the value function. So instead of directly saying, I'd like to act in this way or in another way, the value function only tells me whether I like this state or not. So it's slightly different. You may say, okay, if I like being in a particular state, I should just make an action which maximizes this value, right? But it's not obvious, it's slightly different. And the training techniques are different. So there is exploitation versus exploration problem. I said that when you'd like to maximize your reward, so in a sense you'd like to act to get as much as possible, but is it always the case? Do you always behave like I want as much as possible immediately? Not necessarily. And one of these things is when you learn something new, you don't want to effectively exploit the current best strategy because you stop learning. You just walk the one path which maximizes the current reward according to your value or whatever, but you don't learn anything. So the other spectrum is where you effectively randomly walk around, you learn a lot, but you almost never, you rarely find the optimal path. Since random path is rarely the optimal, you can not find any reward. So if you don't find reward often, you don't know what to do again. So these are two spectrums of the problem. And of course, there's something in between. So the most basic in-between technique is called epsilon greedy strategy, where with probability epsilon, you choose an action at random. And with 1 minus epsilon, you just exploit the current best strategy. And there's, I called it, actually authors of the paper I'm going to refer to, and we called it the leaf problem. It's a problem that when I'd like to learn something, there are things that I cannot affect. No matter how I move or what I do, the leaves just move around and so on. So it's a problem of effective exploration. When I like to explore and learn something useful, I don't want to watch leaves how they move. It doesn't make sense because I can never affect them anyway. So that's one of the problems when you learn, that someone may think, okay, something changes, the entropy changes, I should learn what's going on. And that's not always the case if I can't effectively use it, exploit it. And these guys tried to address this problem. They're guys from, I guess, UC Michigan. They wrote a paper, Curiosity-Driven Exploration by Self-Supervised Prediction. And there is a movie about it, but if we watch it now, I believe it would be difficult for us to understand that. So I propose to postpone that in the end when I explain all the details of the paper. I seriously love this paper. So, key insights. You don't see key? You do? Great. So the epsilon greedy strategy, or another, say, slightly smarter strategy, is not to move at random, even once in a while, but say you have the distribution of what to do. Say 1/4 I go left, 1/4 I go right, 1/2 I go forward, whatever. So you may say, okay, you don't always go forward, but with probably 1/4 left, 1/4 right. It's called softmax strategy. But it still doesn't work. It's pretty much walking at random. It's simply not effective. So what you'd like to do, you'd like to explore novel states, obviously, but you'd like to reduce the error uncertainty in the agent's ability to predict the consequence of its own actions. So it's like the leaf problem. You'd like to exploit that sometimes you can affect the environment and sometimes you can't. So we only predict those changes in the environment that could possibly be due to the actions of our agent or affect the agents and ignore the rest. So easier said than done. And the goal is to generate an intrinsic reward signal based on how hard it is for the agent to predict the consequences of its own actions. I'm saying that that's the problem we'd like to model. Obviously, it's not like we solve this problem and exploration's done. No, there are other problems, but basically they try to address this issue. Yeah, so that's the model. It looks difficult. Obviously, it's not. Don't worry. But first, just focus on the left side and think that you have a policy with respect to which you behave. The policy gives you an action you'd make, and the action affects the environment, and the environment gives you another state. So you pretty much just play the game. You play the game. When you play the game, the previous state, the next state, and the action you've made goes to the intrinsic curiosity module. So you explicitly module the intrinsic curiosity, and I explain that in a moment how you model that. But you must think of that you play the game, and some of the information, let's assume you keep that in your head, and you sometimes feel curious. Okay? And how and why you feel curious. Here we will slightly speak slower, I would say. So the key insight is to see which actions you affect the environment, and by which actions you can affect the environment. And the idea is to encode the state into some features, and those features, this phi, should represent only those things you can effectively affect. Okay, so you have encoding, you have a state, it goes through some for now it's a black box, which gives us features, and let's assume we can force the model so that these features hold the information about things I can affect. So how do we force model to learn this effective representation? How do we force the model not to learn leaves or whatever, but to learn that I can move laptop or whatever else? They do that by inverse model, in the sense that we'd like to predict an action that caused that. Okay, we have two encodings, one state and the second state, and the inverse model tries to predict an action which changed the environment from one state to the other. So if we are able to predict the action I caused and the change in the environment, then it's a desirable action. But there is also a forward model which takes an action, takes the current features, and tries to predict these features. So one model tries to simply predict those features, and another one asks whether it's an interesting action or not. And if those features differ, the features from the forward model and the features from the state, then we say that it's interesting. Okay? I'm not sure if it's clear. It's really difficult when it's said like that. I understand that. But like I said, you'd like to think about it that at one point you'd like to think that you have an action which is somehow important to us, and on the other side you just try to predict the features on the environment. So you forced the model to learn the features which encode only the important actions, and if you can't predict the actions, but it's learnable, so there's a difference. At one point it's learnable, but you can't predict it, then it's interesting. So how do we train the model? There's an expected reward, so it's straightforward. It's just expected reward when you act with your policy. Your policy is your behavior, so we'd like as much as you can get. It's obvious. Another thing is you minimize the difference between the true action you've made and the action predicted by the model. So you'd like to be able to predict the action. So you want to force the model to learn those features. And the last thing is you compute the difference between those features, so it's straightforward. And how do we train the agent? Who's the agent who's playing the game? So it's a neural network, so it's deep reinforcement learning. If you don't know what a neural network is, or you just don't want to focus on that, think of a neural net and all these black boxes actually, forward model, features model, inverse model, whatever, it's just a function. Neural networks have the property of being a universal approximator. So you can approximate actually any function on a compact set. There are theorems, but from our perspective, why can it approximate anything? Because we feed that with the data, we update the weights, and it's able to effectively work as the function we want. So the agent is a neural network. It gets a state. After some feature extraction through convolutional neural networks, there's an LSTM to catch the temporal difference. So it's long short-term memory cell which catches temporal differences. It's a recurrent neural net. It's getting technical, but you don't have to remember this detail. And in the end, you'd like the value of the state. So I get a state, I think about it, I output a value of the state, and an action I will make. Okay? And it's trained from visual input, from downsampled images. So it's a direct visual input. And the frames are concatenated, because when I move to catch the temporal difference, you get a few frames, and you feed the model directly with a few frames at the same time. And it's trained with A3C is an algorithm with LM optimizer. Forget it. And these other forward model, features model, inverse model are other neural networks. It does compile. Maybe I will skip the details here. And how was the idea tested? It was tested on the DOOM environment, PyData actually it's called, where you have the 3D model of actually it's a game, it's a 3D game. So the DOOM setup was, you started in a room and you were supposed to get to the goal. Actually that was interesting for the researchers, whether the agent will get to the goal or not. But he didn't always get reward. That was not the case. So after 2,100 steps, there was a termination. The episode ended, and another episode started. And to get from the 13 or 17, I don't remember, room, it was approximately 250 steps. I just want to give you the idea about the numbers. When you behave optimally, it's 250 steps. But if you don't behave optimally, then obviously it's really a lot of options. And you got one, yeah, actually in this setting, you got one for the goal. In other settings, you won't. And for the important thing is that for walking, you got nothing. For walking, you got nothing. Only in the end, if you got to the goal, you get one reward. And the performance comparison, when dense reward is a setting where the agent was randomly spawned on these blue dots. So it's not that difficult. Usually it's closer to the goal. We see that this model is called ICM plus A3C with this features extraction. Performed best actually. It was best. When it was trained on the raw pixels, so there was no this features extraction, intermediate features extraction, these features which are interesting for us, then it behaves slightly worse. And the vanilla A3C is the worst algorithm. So it works. But see the numbers, it's number of training steps in millions. So it's not like it's all solved and done. It's still out to do. And that's another setting where you start from this slightly farther room 13. And again, okay, you see that from pixels, it's actually even slightly better than with curiosity. Maybe curiosity here is not that important. It's not that far away from the reward. It's perfectly fine. But what happens when we start from the last room? Those other algorithms, row from pixels and the vanilla A3C can't even learn. It becomes extremely difficult to finally find the farthest room, because these few rooms away gives extremely lots of possibilities to move, still a lot. And only the ACM plus A3C learns. And the authors check the uncontrollable dynamics, so how the model generalizes, because it's clear of machine learning. You can train the model on data, but if it doesn't generalize well to new environments, new things, whatever, it just doesn't make any sense. So they randomly occluded, it was random noise. They occluded some of the visibility of the agent. And you see that from pixels, it was extremely difficult for the agent to learn. And with ACM plus A3C, it still performed well. And another thing they checked is when there is no extrinsic reward. So you don't get anything for getting to the vest in the end, but you just get the intrinsic reward for walking. The only thing you get was the reward we've previously seen. If the action is interesting, if I can't predict it, then I try to perform the action. And we see that with random exploration, it rarely gets out of the first room, and with the internal reward only, it explores significantly more space. And another thing is with a different train setup. They pre-trained the agent on a different map, and they tested the model on another one. When the agent was pre-trained, it didn't get any reward. It was again only curious and only walking, trying to make these actions. And they asked, okay, what would happen in the test map, whether it helps the agent or not, whether it generalizes to different rooms. But they fine-tuned the algorithm with a reward. So in this second scenario, it's not a test scenario yet. It was also slightly trained on this other room. And if you try to train the algorithm from scratch, it didn't work. When it was pre-trained and fine-tuned, again, the algorithm performed well. And another game they've tested the algorithm on was Mario Bros. So you play the first few levels of the Mario, and they checked whether, again, how it generalizes and how the agent plays. It was evaluated only by the distance the Mario covered during the game. So it's somehow, okay, you may say that in general, the idea is like explore, and in Mario pretty much you don't get nothing unless you just walk, right? So it's pretty much similar in a sense. But still, the agent could explore some it could learn nothing. It could not be. It could be not able to explore. So the Mario generalization was strange in the sense that when the agent was trained on the first level, then after it was fine-tuned, so it was also trained on the second level, it obviously performed better. But it performed better even when it was fine-tuned on the second level, it performed better than if it was trained only from scratch on the second level. So it's okay, it's fine. You've learned something from the first level, you perform better on the second level instead of if you tried to play only on the second level. That's perfectly fine. But strange thing happens on the level of third, where when you run the algorithm only after training on the first level, it performs better than when it's additionally trained on the third level. And honestly, authors can't really precisely explain why it happens. They suggest that difficulties between the levels are different and so on, but it's still some room for improvement. And they compared the algorithm with other state-of-the-art paper. It's based on variational information maximization, maximizing exploration. It's definitely different technique in the sense it maximizes entropy. And I haven't read that personally, and I don't think we have time to just try to even delve into it. But it turns out that the algorithm ICM plus A3C outperforms it. And there is implementation available on GitHub, so I suggest running it. I haven't done that yet, but I will. Thank you.
Thank you so much for your talk. Now we have time for 2 questions.
I have just one basic question. You mentioned that there are those 2 basic approaches. One is you get -1 for each step and 0 at reaching the goal, and the second is you get 0 for each step and 1 for reaching the goal. So in the second approach, the actor is not punished or penalized for walking, basically. So the agent can greedy check all the paths. Is not motivated to find the nearest path to the goal. Am I thinking correct?
Yeah, I guess you're right.
So
Yeah, this setting may.
So it's basically, if the agent is not motivated to find the nearest path, the closest path to the goal, then he can find he can find or select not optimal solution. Am I missing something or not?
No, I guess you're not. I guess it's all about exploration, whether you get to the final room or not.
Really? So you can select a very long path and it's still okay?
In this particular setting.
Ah, okay. Okay, thanks.
Thank you. One more question. This one? Oh, all right, sorry. Okay, so I guess the rest of the doubts or questions will be left for the after party. So thank you, Paweł, one more time.
Thank you.
Big applause.